Okay, now can you hear me? Can you hear me?
Yeah.
Yeah. So you are absolutely right that cobalt is occurring in +1 oxidation state. Can you tell me about the total valence electrons of this complex?
Um. Total valence electron of cobalt.
Of this complex, the whole complex.
Complex. 9 plus 4. Wow. Nine. 18 electron.
Right. So now I will tell how we can calculate it with both the methods. So what method you have chosen to calculate the total valence electrons? Is it a neutral method or the ionic method?
Uh,
In
neutral method.
You are taking that of metal as a neutral. You don't consider the charges. In ionic method, you consider the charges. So we will just see quickly how both of them will give the same answers. So in neutral method, when we have Cp, cobalt, and CO whole 2, so we know that in neutral method, Cp is not, we are not considering the charges, so it will only contribute the 5 electrons. Cobalt is D7 4s2, 3D7 4s2, so we will consider the 9 electrons without considering its oxidation state. So here, since we already know that cobalt is in +1 oxidation state, so we are not considering here because this is called a neutral method. Okay. Now the carbonyl is anyway having the 2 electrons, so 2 into 2, that is 14 plus 4, it gives you 18 valence electrons. Now if I am having this ionic method, so in case of ionic method, you need to consider the charges on everything, be it ligand or the metal. So now Cp will exist as a -1, that means it will now give 6 electrons. Cobalt was in +1 oxidation state. Earlier it was 9. Now it will give 8 electrons. Carbonyl is having 0 charge, so it will continue to give the 2 electrons. Now if we will consider Cp, cobalt, CO whole 2, Cp is 6 electrons, plus cobalt is 8, 2 into 2. Again, this is 14 plus 4, that is 18. Sometimes what happens, students do confuse all the things and they will consider the 6 electrons from Cp-1 because the charge has to be considered, but they will not consider the oxidation state of the cobalt, and they will end up having the wrong answer at the end. Because if it would be 9 and this is 6, that is 15 and 4, that becomes a 19 electrons, which is not a stable thing and the wrong answer, obviously. So this is where when we know the oxidation state or the contribution of Cp as a 5 only, then we get to know, or it could be framed in a different direction. If it has been given that cobalt is in +1 oxidation state, how do you calculate your hapticity of Cp? Whether it is coordinated as eta1, or it is coordinated as eta3, or it is coordinated as eta5. So now you can calculate easily, right?
We need to know the hapticity, or else we can.
Any of the things you need to know at least one answer. Either you should know the total valence electrons, or you should know the metal oxidation state, or you should know the hapticity of your Cp thing. For example, if I have that, okay, this complex is making an 18 valence electron thing, right? So I don't know the contribution that is coming from the Cp. Most importantly, we should know the 18, the total valence electron. So I will consider that Cp cobalt CO whole 2. I will take it as a x. X is nothing but the contributed electrons or total valence electrons that it is contributing. So that I don't know. The cobalt that we know that it is contributing 9 because we are talking still about the neutral method. And CO that is 2 into 2 and it will form 18. Then X plus 9 plus 4, 18. X plus 13. Then X equals to 5. And 5 will only come when it is in eta 5. Right. Now, if I will do like this way, if I have the Cp and cobalt CO whole 3. Now, what would be the, and if I have Cp cobalt CO whole 4. Now, what would be the hapticity of in B and in C? You can just try. That is straightforward. The first that we got to know that in this particular case, if we have Cp, cobalt, CO whole 2. Now I've increased the carbonyl to CO3 and this is CO whole 4. Still they are making 18 valence electrons that I am giving you the choice. Now how you will get to know about in what hapticity Cp is now. Is it still maintaining its hapticity of 5 or it has reduced to 1 or reduced to 3 or any other thing? Hello? Are you solving or should I start explaining?
Yeah, I am starting. I am trying to solve.
Yeah, you just solve in take 2-3 minutes and then we will discuss and explain properly.
In the B, hapticity will be 3.
And in C?
Yeah. Yes. Hapticity is 1 in C.
Excellent. So here it is eta 3 and here it is eta 1. Also, if you just don't even see and calculate the total thing, na, you just remember that earlier what we found Cp, cobalt and CO whole 2. So here we have included one more carbonyl and one carbonyl will bring 2 electrons. If it is still maintaining the total valence electrons and one carbonyl is extra coming with 2 electrons, then 2 electrons has to get reduced from the Cp. So earlier it was 5, then it will become 3. Now in C, we have added one more carbonyl, which will bring 2 electrons. It was earlier 3, now minus 2. Then ultimately it will be 1. So if not, then we need to just calculate through the total valence electrons. So Cp contribution we still don't know. Cobalt will give 9. This will give 2 into 3, 18. And X becomes 18 minus 15, that is 3. So that's why it is eta 3. And here, in this particular case, it would be X plus 9 plus 8 and 18. That will become X equals to 18 minus 17, that is 1. So this is way, if you know one single answer, like total valence electrons, you can calculate anything, be it its oxidation state or the contribution from the ligand, the hapticity of your ligand, the oxidation state of other ligands that has been attached. So this becomes very feasible and easy. Now, see what we started with. This is just a substrate. And these 3 or 4 questions can come from just the substrate itself. That is the way that questions are going to become in exam also. So you should do appear in the exam and try in that particular way. Okay. And during that time, try to eliminate all the options, as many options you can eliminate. For example, if 3 particular questions have been there, and if you have solved this part, so how is the number of electrons and what is the hapticity state, and just be very attentive, and like one carbonyl is coming to picture, so 2 electrons has to be reduced. Another carbonyl has come, and then again hapticity would be reduced, because only the CP which is having different hapticity and the chances, that is going to reduce the number of electrons. Other things are not going to change, because the oxidation state is not going to be changed, as carbonyl is not bringing any particular charge. Okay. Now we will come back to the main question. So the question was, this was a substrate, as we now know that it is an 18 valence electron species where cobalt is in +1 oxidation state and CP is in eta 5. See how many information we can calculate and get from a single thing. So here we are having an alkyne system. R could be anything. And we should not ignore this heat. Heating will always lead to some different kinds of products. So it has been given that one of the products would be this benzene ring having the substitution with R. And what is the one? So these are the 4 options. And those who have read the lectures and gone through the lectures, they know already that whenever the heating is there, these alkyne systems, they tend to undergo the cyclization. They will form a cyclic product. For example, here, so if I have this RC triple bond CR. So if I'm taking the molecules now, for example, if I have 2 molecules of it, like this, RC triple bond CR and C triple bond C. So this is 2 + 2 oxidation, 2 + 2 addition. So this will come only in presence of heat or the photochemical that we read in pericyclic reactions. Okay. So now this bond, this is a pi bond, and this will go, and this is a pi bond, and this will go and attack your this carbonyl. And because its oxidation or the number of bonds has been increased on the carbon, now this pi bond and go and attack with your carbon. So ultimately what will happen? One bond has gone from here to make, if I'll just give a symbol 1, 2, 3, and 4. So this is having a substitution of R. This is nothing but this 4th bond. So now one bond has been newly formed between 2 and 3 and newly formed between 1 and 4. And the earlier triple bond between 1 and 2 and 3 and 4 has been reduced from 3 to 2. So now this is 1, this is 2, 3, 4 with R. So the new bond has been formed between, that I will show you with a different color, C2 and C3. This is one single bond, and C1 and C4. And this will remain as it. So what is this kind of structure? This is nothing but a cyclobutadiene. Right? So you are now having this particular system where R, and R is there. And if we are having 3 molecules, so there are 3 alkyne groups, and still you are giving heating. So what you will get? Now arrange it in like this manner. R. So I am naming it as 1 and 2. Now the R, this is 3 and this is 4. And again, this is 5 and this is 6. Now again the transfer will happen. So this bond will attack on this carbon. This will attack on this carbon, and here it will attack on this carbon. So the now new bonds would be formed between 2 and 3, 4 and 5, 1 and 6, the new bonds. And 1 bond is going to be gone from 1 and 2, 3 and 4, 5 and 6. So ultimately what it will form? C, double bond C, single bond C, double bond C, single bond C, double bond C, and this single bond C, R and R. So all the carbons are having substitution. So this is 1, 2, 3, 4, 5, and 6. This is nothing but your benzene ring, that arene ring that we are having, with the substitution of R groups. So ultimately, what our goal was, because this was having an alkyne center and we were giving the heating. So the first product that it could give, if two molecules are undergoing the 2+2 additions, that will give you the cyclobutadiene. And the other product that they have already defined, that three molecules will go and give you the arene structure. So what could be the possible answers? Like out of the four, what is the only answer that you can look at? You can try. Hello. Okay. So just don't consider it as like, okay, this product has come out, like Arene group has come out, so that cyclobutadiene is also to come out. So what we should not ignore this particular substrate also, which is already having this carbonyl, and this CP ring. So one more thing that we need to define here. Firstly, the metal CP bond is very strong. Also, only those ligands can be replaced by some other ligand which is contributing the similar way, because the charge is actually maintaining. For example, if you will see, this is an 18 valence electron, right? So it is now coming, this was in +1 oxidation state, here it is shown in +2 oxidation state. Here if you'll see, this is a neutral complex and the oxidation state has not been defined. Most likely it is only +1 oxidation state, because cyclobutadiene is not going to have the more charge on it. So now if you will see that carbonyl and carbonyl, this is 2 electrons and the other one is also 2 electrons. So if you will see, when both the carbonyls are going out, so they are having a loss of 4 electrons, and the 4 electrons will only be dealt if we are having this kind of system, because we cannot ignore that kind of this heating over there. So it will form this cyclobutadiene system, which is having the 4 electron contribution, and they will replace the 2 carbonyl groups over there. So this is the only, the D1 is the only right option over here, because we cannot have this, if for example here, the 4 these carbonyls are being replaced, CP as it is, it has to maintain its 18 valence electron also. If you will calculate here in this particular state, it is 5. Cobalt, I'm talking about the neutral method. Cobalt is in 9, and this C6H6 or R group R6, it will give you the 6. Now, if you calculate here, this will become your 20 electrons. So this is not the right option. Similarly, here, if you are now, this could also be an option, but because this is 5, this is 9, this is 2, and this is also 2 electrons. Here it is 5, 9, 2 electrons, 2 electrons. Here also 5, 9, and 4 electrons. So all these A, C, and D options are maintaining 18 valence electrons, should not be disturbed. But we cannot ignore this thing where we are having heating and this reagent, the alkyne group. In heating, it will form this tricyclization or dicyclization product. Tricyclization will come out as it is, because it is a stable aromatic compound, and the dicyclized product, which is the cyclobutadiene, that will go and coordinate with your metal and will maintain that 18 valence electron species. So is it clear, or you have any doubt? Hello. Ratna, you are muted. Hello. Okay, so I hope this is clear to you. We will just move to the next question. So now we need to find out the metal-metal bond order in this particular complex. This is a very important question. If you can unmute yourself or can put a message in the chat box, then I will be able to know whether you understood the things or not. Okay. So now, if it would be better if you can just unmute and should try to solve this question. Now, this particular dimer complex has been given where eta 5 C5 Me5 whole twice Re2 CO whole 3 complex has been given, and you need to find out the metal-metal bond order. So the metal and metal, how they are having, how many number of bonds they are having. So bond order is nothing but the number of metal-metal bonds they are having. So that you need to identify. And for that matter, you can consider both the metals, the rhenium is making an 18 valence electron complex. So now you need to find out like what would be the total number of valence electrons. So just let me know the answer. That would be great. Then we will solve it. Okay. Okay. So now since we have this kind of systems where eta 5, C5, Me5, this is 2 in number, rhenium is 2 in number, and carbonyl 3. So if one metal is having total valence electrons as 18, the other metal is also having the same number of valence electrons. So total valence electrons now become 18 plus 18, that is 36. Okay. So the calculation will start. We don't know how many number of metal-metal bonds are there. So if I will say X is the number of electrons for the metal-metal bonds. So if it comes as 2 electrons, that means metal and metal is having 1 bond. If it is 4 electrons, that means there is a double bond between metal and metal. If it is 6 electrons, it is coming as 3. Because 1 bond will give you the 2 electron contribution. So I am taking X as the number of electrons that is coming from the metal and metal. Now, we have the 5, C5, Me5. This is nothing but your Me. Substitution of your hydrogen on the CP as, and this we call it as a CP star. So short form, so don't get confused. This is 2 in number, rhenium 2, carbonyl 3. You need to tell me what is the total valence electrons of the rhenium. Can you please tell me? Okay, so rhenium comes in the group of manganese. So where they are having a valence electrons of D5S2, that means 7. So here, if I am considering this C5Me5 will also give the 5 electrons, and since 2 are in number, that is 5 into 2. Rhenium is 7 electrons, which is into 2. Carbonyl will give you 2 electrons, and there are 3 number. And X is the number of metal-metal bond electrons that we have to find out. And the total value is 36. And if I will say over here, so 10 plus 14 plus 6 plus x equals to 36. This will give you as 30 plus x equals to 36. And x will come as 6. So as we already discussed, that if x equals to 2, that means single bond. If x equals to 4, it will always come as an even number because one bond is 2 electrons. If it is there, M triple bond M. So therefore, since our answer is x equals to 6, so rhenium and rhenium, they are making triple bond. So metal-metal bond order is P. So the question was the metal-metal bond order in this particular complex. We got the answer as 3. So I will explain it again. So here we were having this complex and we need to understand, we already know that rhenium is 18 valence electrons. So both the rheniums are making 18 valence electron complex. So the total valence now become as 36. So while calculating the metal-metal bond order, you need to consider the total valence. So you cannot start with the single 18 valence electrons, because if you are considering the 18 valence electrons, that is not going to form any bond with the metal because you are only considering one metal. For the metal-metal bond, you need to consider both the metals. That is why total valence electron has to be there. And there we choose that, okay, X is the total contribution that is coming from the metal-metal bonds. And if it comes as 2, that means one bond is there. If it comes as 4, then double bond is there. If it comes as 6, then it will be 3 bonds because one bond is giving 2 electrons. Then what we saw that C5Me5, it is going to give you the 5 electron contribution because we are considering the neutral method. They are 2 in number, so 5 into 2. Rhenium belongs to the manganese group, which is having 7 electron valence electrons. So 7 into 2. Carbon will give you 2 into 3. So 10 plus 14 plus 6 plus x. X is number of bond electrons, which we have not known so far. We will get to know once the calculation is done. And it has to be equated to 36, not 18. So once we calculated, x comes as 6. So once x is coming as 6, that means it is forming a rhenium triple bond. So hope now this is clear. Or you want me to repeat it? Okay, great. So we have still half an hour left to finish off the slide session. So if you have any query regarding these questions, you can just let me know, because we have mostly taken the questions regarding the number of valence electrons, the hapticity, the oxidation state of the metal. And then I can take a random question from any of the assignments, which will also help to understand the concepts even more. And don't worry about the lecture. I will just share this video and also these lecture notes, and you can get to have this access anytime, and you can just go back and revise the concepts again. So if there is any question, then I can just wait for some few minutes and then we can shift to some other question. So I will just show you what we have read so far. I might not be able to see your thing, so I will just put it like this way. So what we actually covered here, firstly, in the first question, that we have to find out the total number of valence electrons in this particular center, that we have seen that even after calculating the total valence electrons, either you need to know the hapticity or the contribution that is coming from the ligand as well as your metal center, then only you will calculate your valence electrons. Also, sometimes you need to know the geometry of your metal center, how it is coordinated with it. Again, it will end up, I don't know what is happening. Sorry for the inconvenience. The meeting will end up in 9-10 minutes again. If you want to join, you can rejoin the same link. Okay, anyways, so from this method, these are the all ligand systems that we have covered in the starting 4 or 5 lectures, starting with the allyl system and going to the butadiene and CP ring, CP star, the arene system, C7H8 and C8H8, which is the cord. So that all of them we have covered already, and they all mostly they are doing the same or more or less the same chemistry. And then we saw like, okay, with the total valence electrons, what the benefits, what kind of benefits we are having. We can calculate the oxidation state, we can calculate the number of metal-metal bonds and the hapticity. So all these 3 types of things with the valence electrons I have shown you for today's examples. Like we can get to know about the oxidation state that we just saw with the nickel one and the manganese one. Metal-metal bond order, we just solved the question for the rhenium thing, how it is coming is 3. And also the hapticity of the ligand, whether it is coordinated as eta 1 or eta 5 or eta 3 with different complexes with the number of carbonyl groups, how the hapticity is changing. And then we calculated how it is going to be in eta 3 or eta 1. And then oxidation state also we calculated both with the neutral method and the ionic method. Here we have to be very careful when we are taking neutral method into consideration. You need not to take any charges. The metal has to be taken as a 0 because we are talking about the neutral method. The CP or any other ligand for that matter, no charges there. But in ionic method, you need to be careful when you are seeing that, because the CP ka charge should be considered, the metal ka oxidation state has to be considered. Everything has to be taken into consideration for that matter. And then again, if we know the charges directly, we can get the oxidation state from here. That CP is -1, C3PH3 is +1. But there you don't need to memorize anything. You just have to understand the ligand system. For example, here that C3PH3. So why I have taken the positive charge here and CP as a -1. So this has already been explained. It is because of the aromaticity that we talked about. So when we have this minus charge in here, so when once it is taking or it is having a minus charge with it, like it becomes a C5H5 minus, that is 6 electrons, then it becomes an aromatic system because the total number of electrons is 6. And from the Huckel's rule, we have this 4n plus 2 pi electrons rule. So if I consider n equals to 1, it becomes plus 2, and this becomes 6 electrons. That means it becomes a aromatic system, so which is highly stable. So that is why it becomes very important to assign the charges. Why the minus charges with CP, not with plus charge? Because if it is having a plus charge, then it will be reduced to 4 electrons, which is not making an aromatic system. So this does not come to as an aromatic system, and the stability will be gone. Similarly, if I am considering this C3PH3 system or C3H3 for that matter, so it is having this bond and this positive is there, then if it delocalizes over there, now the positive charge would be here. And if it again delocalizes over here, then the positive charge would be here. So it is moving in all the systems, and ultimately it will give you a positive charge here. Why? Because 4n plus 2, it is also an aromatic system, 4n plus 2 pi electrons. If we consider n equals to 0, then it will become a 2 pi electron system. So either it could be 2 pi or 6 pi, or it has to be 4 into 2, 10 electrons and something like that. So these are all the aromatic systems. So that we have to take into consideration. And from this way only, we get to know whether CP is having a charge of -1 or +1. This C3PH3 is having a charge of +1 or -1. It is not like we have made it and randomly we are giving the numbers. It has to come from a particular rule. Similarly, if I will ask that what this system is having, . So this is a quad system. Which one pi bond is contributing to one electron? Can you please unmute yourself because I didn't understand your question? Where I have taken the one pi bond. Pi bond is taking as a 2 electrons only. Can you please refer to the question? Which question you are talking about? Are you speaking? Because I am not able to hear you. You said just write in the chat box which question you are referring to. What I have missed in CP contributes 5 electrons and like that. Yeah, CP contributes to 5 electrons, but the pi is considered as a 2 electrons only. It is never one pi bond will never give you the 1 electron. It is always 2 electrons. Where the pi bond has contributed 1 electron, I'm not getting your question. Why we add 5 electrons in 18 electron group? Because there we are considering the neutral. When we are talking about, see, that is why I was saying that don't get confused with that system. So when we are talking about the neutral method, there we only consider the number of electrons or the carbons that are being involved in coordination of with the metal. So there are only 5 carbons. We cannot go beyond that 5. It cannot become a 6. 6 only comes when the ionic method we consider or the charge we consider, because that one extra electron is coming from the negative charge. That is not coming from the carbon coordination with your system. You understood? This has come into picture. Earlier it was like this way. So if I'll take like this, so this metal. So when this metal can bound with your this particular metal or this metal or this side or this metal, we don't know which is there and from where it is getting coordinated. So we take it as okay, all the 5 carbons are like similar in position. But when we are taking the ionic method, the negative charge is coming, and that's why we call it as a 6 electrons. So there are 2 different methods. So generally, when the neutral method is being considered, we have to just count the total coordination with how many carbons it is coordinating, whether it is eta 1 or it is eta 3 or it is eta 5. That would be an odd rule in this C5. But when we are talking about the ionic system, then you need to inculcate your charge also, which is making it aromatic. And that's why the 6 electrons comes into picture. Because if, as I was telling you earlier, like NMR will give you this kind of system only like one, where it is. Yeah, here I was showing you, right? So here, because the carbons and the fluxionality, that is why the fluxionality term comes into picture, that even if we see that it is coordinated with one metal, but it can go easily to other metal side also. So then this will become a single bond, and there the pi bond can delocalize and go over there. So all the 5 positions will become very similar with each other, and therefore the NMR cannot detect it. But the negative charge is already there when we consider the ionic method, because it has to get completed its this aromaticity. That stability has to come into your CP ligand. So generally, CP ligand is being treated as a CP minus 1 if we are talking about the ionic charge, and there it will give you the 6 electrons. But if you are just taking the neutral method, but because in neutral method you are not considering the oxidation state of a metal. Agreed. I will show you here where we have that manganese. Manganese. Okay. Here it is in 0 oxidation state. for this, but yeah, okay, here. So here also it was having a CP ring, right? So if I'm taking an 18 valence electron, did I consider the cobalt as a +1 oxidation